Hello, everyone, and welcome to the lecture on Inorganic Nomenclature. IUPAC, or the International Union of Pure and Applied Chemistry, derived a systematic way of naming chemical compounds. The reason they derived this systematic rules, if you will, for naming chemical compounds in 1957 is because there were so many compounds with common names, millions, that scientists just couldn't memorize every single one of them. So they derived principal divisions and subdivisions with rules for naming acid compounds, base compounds, ionic compounds, and covalent compounds. And the subdivisions broke these compounds up into binary, that is, compounds that consist of two kinds of atoms, tertiary, compounds that consist of three kinds of atoms, and usually one of those is oxygen, and then hydrates, or compounds that have water molecules as part of the composition of the structure. Now, these aren't compounds that are dissolved in water. These are compounds that are solids, solid salts, but as part of their substituent composition, H2O molecules are included. The principal divisions include acid compounds, and those are compounds that begin with hydrogen. Base compounds, or in this case, we're going to name hydroxide base compounds. Ionic compounds that consist of a metal and a nonmetal, or we could alternatively say they consist of a cation and an anion, because metals have a tendency to give up electrons to get the electron configuration of the Nobel gas closest to them, and therefore have positive oxidation states. And nonmetals have a tendency to gain electrons to have the electron configuration of the Nobel gas closest to them, and therefore have negative oxidation states. And then there are covalent compounds, which are compounds that consist of nonmetals. We need to go over some preliminary information before we start naming compounds. The first is oxidation state, which you're already on top of. You already know how to calculate oxidation states, the charge, or what we would say is the apparent charge of an atom or an ion as that atom or ion begins to form a compound with another atom or ion. We call it an apparent charge because it isn't like the charge that you have, per se, on a polyatomic ion, where that species exists with a negative or a positive charge. It's an apparent charge because it's a charge that a species, a chemical species, will acquire as it approaches another chemical species that it's going to be involved in a reaction with, i.e., bond formation. There are stems that are given for compounds that are non-metallic. There are Greek prefixes given for binary covalent compounds. There are Roman numerals, which are used when we have variable charge, and common ions, the polyatomic ions, those ions that you're going to need to commit to memory. Here's a list to get you started, and you can see this big memorize at the bottom. You won't be given a table of these polyatomic ions for the exam. They've got to be commit to memory. And so there are a few here to get you started initially memorizing both the formula and the name, but there are many, many more. These just happen to be some of the most commonly used. You don't have to memorize every polyatomic ion on every table that you see. You won't even have to memorize all of those that are listed in your textbook, but you'll know which polyatomic ions you need to memorize beyond this slide, because the worksheets that you're going to be going through and the videos you're going to be watching will show you or demonstrate for you which polyatomic ions you'll need to know. So let's go back and review oxidation state or oxidation number. The oxidation number of an element in its free state is 0. As you know, every species on the periodic table has an oxidation state of 0. The chlorine in Cl2 is 0. Iron, for example, has an oxidation state of 0. All of these diatomic gases, that is Honkelbrief, that you memorized. And here's another reason why you had to memorize those. All of those diatomic gases, or there's another acronym, have no fear of ice cold beer, those are the diatomics that you memorized. All of them have a zero oxidation state for either atom that's involved in the bond. And here's the reason why. If we look at chlorine, for example, if for chlorine we were to break this bond, each chlorine would take with it the same amount of charge when that bond is broken, because each chlorine has an identical nucleus that's attracted to negative charge. And therefore, each chlorine would have an oxidation state of 0. Now, if we had something, for example, like HCl, and we broke that bond, this wouldn't be the case, the same case that we had with Cl2, because the chlorine is much more electronegative than the hydrogen. And so if we were to break that bond, the chlorine would take with it more negative charge relative to what the hydrogen would take with it. And therefore, the oxidation state of the hydrogen is +1, and the oxidation state of the chlorine is -1. The oxidation state or oxidation number of a monoatomic ion is equal to the charge on the ion. So Fe2+ has an oxidation state of 2+. If we had Ca2+, calcium 2+, it would be an oxidation state of 2+. If we had Na+, sodium would have the oxidation state of +1. For compounds, the more electronegative the element, the more negative the oxidation state is going to be. So if we look at a compound like potassium chloride, potassium is way over on the far left of the periodic table. Chlorine is way over on the far right of the periodic table. Chlorine is very, very electronegative. In fact, all of those halogens need only have 1 electron to get the noble gas configuration that's closest to them. And so this creates a situation where you have a very, very electronegative meaning a species that wants electrons and wants negative charge. So those halogens are very, very electronegative, and their oxidation state is going to be negative. On the other hand, those species on the left side of the periodic table want to give up electrons to get that electron configuration, the noble gas closest to them. So they will have a positive oxidation state, or you could say less electronegative. Oxygen is usually 2- in compounds, but if we have something like H2O2, which is a peroxide, then oxygen has this one case where it doesn't have an oxidation state that's -2. And if we calculate the oxidation state of hydrogen peroxide, we know that the hydrogens have a +1 charge because it's written first, and by convention we write the cations first, or the metals first, and in this case hydrogen is behaving like a metal. So that would be +1 oxidation state times 2 gives us +2 contribution of charge to this compound. That means that those 2 oxygens are going to have to give us -2 in order for these 2 oxidation states to sum to 0 or be neutral, because H2O2 is a neutral compound. Since there are 2 oxygens, we're going to take that -2 and divide it by those 2 oxygens that we have, so that we know the charge on each oxygen. And the charge on each oxygen then is -1, meaning the oxidation state on each oxygen in a peroxide is -1. This is the only case that you're going to see in which oxygen has a -1 oxidation state. So if you don't have a peroxide, then you can be sure that oxygen has a -2 oxidation state. The oxidation number of hydrogen is usually +1, as it is here in hydrogen peroxide, but there are some cases in which the oxidation state of hydrogen can be -1, which is why you sometimes see hydrogen floating around on the periodic table. It's generally written on the far left, but sometimes you'll see periodic tables that show hydrogen centered in the middle. And it's because hydrogen has this ability to act like a metal or a non-metal. So under what kind of circumstances would hydrogen be acting like a non-metal? We could have a species like sodium hydride or even potassium hydride. And you notice that hydrogen is written second in both of these chemical formulas, meaning that it's not behaving like a metal, instead it's behaving like a non-metal. Sodium has, of course, a +1 oxidation state, so hydrogen would have to have a -1 oxidation state for this to be a neutral compound. And we know it's a neutral compound because we don't see a charge written right here. Similarly, we don't see a charge written here for potassium hydride. And again, if we calculate the oxidation numbers or oxidation states, potassium has a +1. And that means that the hydrogen over here is going to have a -1 to get charge neutrality when we put this chemical formula together. So when you see hydrogen written second or third, not first in the chemical formula, you know that hydrogen is taking on the role of a non-metal. When you see hydrogen written first in a chemical formula, it's taking on the role of a cation or a metal. The sum of the oxidation numbers with hydrogen peroxide, sodium hydride, and potassium hydride. And so we can calculate the oxidation state or oxidation number of species that we're not sure about, given that we know, particularly, there are many oxidation states for representative elements that are going to always be the same. Then there are some of those elements that can have variable oxidation states. So if we look, for example, at H2SO4, that is sulfuric acid, then we know that we have 2 hydrogens, and we know the oxidation state of hydrogen is +1. So that would be 2 times +1. We know the oxygens, because this is not a peroxide, are going to be -2, and we have 4 of them. So the oxidation contribution or charge contribution here is going to be 4 times -2 for the oxygen. The sulfur is the one we're not sure about, but we can set this equal to 0 and then solve algebraically for the sulfur by just taking this -8, we'll add 8 to both sides of this equal sign, and this +2 will subtract 2 from both sides of this equal sign. 8 minus 2 gives us +6, and that is the oxidation state for sulfur that we've calculated. Now we can do this for a species like a polyatomic ion that has a charge on it. And if we look at phosphate, we know those oxygens, because this is, again, not a peroxide, so we know those oxygens have a -2 oxidation state, and we know from this chemical formula that there are 4 of them. So we can multiply those 4 by -2, and that's the charge contribution of the oxygen to phosphate. Phosphate is the one that we're after. We set this equal to -3 because that's the charge, the overall charge that is on this structure. It's not neutral. It has an overall charge of -3, which means that the charge contribution of every atom in this polyatomic ion is going to sum to the charge on the polyatomic ion. And in this case, again, that's -3. So we have here -8. Algebraically, we're going to add 8 to both sides of this mathematical equation, so that we can calculate what the charge contribution of the phosphorus is. 8 minus 3 gives us +5, and that is the oxidation state of the phosphorus in the phosphate polyatomic ion. So let's do a couple of other examples. Let's calculate the oxidation state or oxidation number of manganese in potassium permanganate. So we know that the potassium has a +1 oxidation state, and we know that there is one of them. We know that we only have one manganese, but we don't know exactly what the oxidation state is of manganese. That's what we're after. And since this is not a peroxide, we know we have 4 oxygens. Each will contribute -2. So when we resolve this, we have -8 and +1. So we take those to the other side of the equal sign, which is 0, because this is a neutral compound. There is no charge associated with this compound up here. So we know it's neutral. So we take those to the other side. We're going to add 8 to both sides, and we're going to subtract 1 from both sides. So we have over here 8 minus 1 gives us an oxidation state of +7 for the manganese. Let's calculate this in a polyatomic ion, permanganate, which is another polyatomic ion you can add to your list to memorize. So if we calculate Mn, we know that there is one of them. We just don't know what the oxidation state is here. And then we have 4 oxygens, all with a -2 oxidation state, and we set this equal to -1 because that is the charge that we have on this polyatomic ion. It's not neutral. We have -8 here when we do this calculation, so we're going to add 8 to both sides of this mathematical equation to solve algebraically. We get +7, which is the oxidation state of manganese in permanganate. And here's the solution for that entire oxidation state resolve of potassium permanganate and permanganate. Another preliminary bit of information you need are the stems for the compounds of non-metallic elements. So you can see that we have group, column, or family 1, group, column, or family 3, 4, 5, 6, and 7 here. And so in group, column, or family 1, hydrogen stem would be hydrogen. In group, column, or family 3, boron stem would be bor. Group 4, carbon stem is carb. Silicon stem is silic. Nitrogen stem is nitro. Phosphorus stem is phosp. Arsenic stem is arsen. Oxygen stem is ox. Sulfur is sulf. Selenium is selin. Tellurium is tellur. Fluorine is fluor, chlorine is chlor, bromine is brom, and iodine is iod. Now these are stems for compounds of non-metallic elements. Let's compare this and let's look specifically at carbon, phosphorus, and sulfur for ternary acids or oxyacids. Now the other stems remain the same, but for ternary oxyacids, the stem for carbon is carbon. The stem for phosphorus is now not phosp, it's phosphor. And the stem for sulfur is sulfur. All the other stems, as you can see, remain the same. Another preliminary bit of information are the Greek prefixes, which you'll use for naming binary covalent compounds. So you can see that the Greek prefix for 1 is mono, for 2 is di, for 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, and 7 is hepta, and students often confuse these two. And one good way to remember it is that 6 has an X in it, and hexa has an X in it. That means the other prefix that starts with an H, hepta, is for 7. Octa is 8, nona is 9, and deca is 10. And we will go up through deca, so you'll need to know, through 10. Nona is a Latin prefix, not a Greek prefix, so we just want to make a note of that. And then also the final O and A are frequently omitted in the prefix if oxygen is in the name. So something, for example, like carbon monoxide. Instead of saying carbon monoxide, we say carbon monoxide, and that should be an anchor name for you because you know it. You know carbon monoxide even probably before you got to this class. Roman numerals are another preliminary bit of information you've got to know. And so I don't know how many of you have grandfather clocks in your grandparents' house or your parents' house anymore. When I was a child, my grandparents had a grandfather clock, so it was easy for me to know my Roman numerals, but a lot of you may not know your Roman numerals. So this table needs to be commit to memory. You can see that 1 is represented by an uppercase I, and then 2 is represented by a double I, and 3 by a triple I. When you get to 4 and 5, you can see that 5 is this V, this uppercase V. If we have 4, we put the I before the 4, and that's supposed to represent 5 minus 1 because the I is on the left, gives you 4. Notice with 6, we have the I on the right side of the V, so that is 5 plus 1 gives you 6. 7 would be the V with 2 I's to the right, and 8 with 3 I's to the right. Since the 10 is an X, then 9 would be an X with an I to the left. In other words, 10 minus 1. Again, you need to commit these to memory. So let's start naming some small binary compounds. We're going to start out with something small that's fairly easy and straightforward, and then we're going to go immediately into something that's rather difficult, ternary oxyacids. I don't want to save the really difficult naming until the end when you're burnt out. I want to go into the more difficult naming fairly quickly so that you can get a grip on it, and then we'll ease up and go to some compounds that aren't quite so difficult. So the small hydrogen-containing binary compounds are gases, and we know they're gases because we give them this subscript of a G in parentheses following the formula, the chemical formula. The generic chemical formula is HX because they start with a hydrogen and then they have some nonmetal that follows that hydrogen, and that nonmetal is just represented generically by an X. In the case of a real formula, that chemical formula we're going to name, X equals Br, which is bromine. So when you're naming these gases, these binary gases, the first word in the name of this compound is going to be hydrogen. So we're going to say the full name of hydrogen. The second word begins with the stem of X, whatever X happens to be, and again in this case X is bromine. So the stem of bromine is brom. And then we're going to convert the INE suffix to an IDE suffix. So the name of HBr is hydrogen bromide. But these binary compounds that contain hydrogen are typically encountered as water solutions. That is, they are called aqueous. So we put an AQ in parentheses immediately as a subscript following the chemical formula, and we know that this compound is dissolved in water. So if we name HBr with a subscript AQ following it, we don't give the full name of hydrogen now. This begins with the prefix hydro, and then that's followed by the stem of X, and again in this case X is bromine, so the stem would be brom. And then we replace the INE suffix with an IC suffix, and lastly we add the word acid. So HBr aqueous is hydrobromic acid. There's one that you probably know very well, and that is HCl. You may have known HCl before you even started this class. HCl is hydrochloric acid. And so if you can remember hydrochloric acid as your anchor, then you'll be able to name any of these binary acids that have hydrogen. Now, the ternary acid compounds, they're called oxyacids also, are a little bit more difficult. Their generic formula still begins with a hydrogen. And they have some X, which is a nonmetal typically, and they also usually contain an oxygen. And often, most often, more often than not, this X with the oxygen is a polyatomic ion. So if you've memorized your polyatomic ions, you'll be able to name ternary oxyacids without any problem. But if you haven't memorized your polyatomic ions, you're going to have trouble with it. Now, if you're given the name and you have to go back to the formula and you haven't memorized the polyatomic ion formula with its charge, you're going to have a difficult time writing the formula from the name. This is going to be the case in most exams. Most exams that are upcoming, including exam 2, I'm going to give you the names of compounds and expect you to transfer those names into chemical formulas and then write the balanced reaction equations. So it's extremely important that you learn how to do this. So let's start with HiO3. And this is derived from the name of the polyatomic ion, including the stem of X, whatever X happens to be. And it's followed by an IC suffix. So for example, IO3 minus is what we're looking at here with HiO3. And we've memorized that IO3 minus is iodate. We will convert that ATE suffix to IC. When we convert that ATE suffix to IC, we go from iodate to iodic. Lastly, we're going to add the word acid, and so we get iodic acid. The prefix per or hypo may be necessary depending upon the oxidation state of the oxyacid that we're looking at. Note that the word hydrogen is not used in naming ternary oxyacids, nor is the prefix hydro used in naming ternary oxyacids. There is a hydrogen there, but we assume it's there because we're naming an acid, and we name this acid based on the polyatomic ion again, including the stem of X. So let's go through some examples of when we might need to add per or hypo. When we have ATE, this is considered to be the representative. We start with the representative, and then we make a determination about whether we're adding oxygens or taking oxygens away from the chemical formula. And that helps us name the ternary oxyacid. So for example, if we add an oxygen to the representative, then we're going to add the prefix per to the name. So let's just look at iodic acid. If we have iodic acid, which is HiO3, and we add one oxygen to this chemical formula, giving us HiO4, then this name would be named as per iodic acid. Suppose we subtract one oxygen from the representative, meaning that I now have HiO2, where I've subtracted from the representative over here one oxygen. This would be iodous acid. Suppose I subtract two oxygens from the representative, and so now I have HiO. Now I'm going to add the prefix hypo and keep the OUS suffix, and so now I have hypoiodous acid. Let's go through another example using the polyatomic ion chlorate. remember the ATE is the representative, and it becomes IC when we're naming the acid. So we change the ATE suffix of the polyatomic ion to IC when we're naming the acid. And we put enough hydrogens in front to give us charge neutrality. Since chlorite has a -1 charge, then we're going to need one hydrogen with its +1 oxidation state to neutralize this compound. So chlorate is our polyatomic ion, which we've memorized with its charge. And so we know we're going to convert the ATE to IC when we name this. We do not use hydrogen. We do not use hydro. So the name of this oxyacid is chloric acid. Now, suppose I add an oxygen. That is, I now have 4 oxygens when my representative had 3. Adding an oxygen means I add the prefix per. So I have perchloric acid with HClO4. Suppose I subtract 1 oxygen. Now I'm going to use the OUS suffix. So I have chlorous acid for HClO2. Suppose I subtract 2 oxygens from my representative, which has 3 oxygens. So I now only have 1. We don't write the 1 here because it's assumed. We know that there's a 1 there. So now with HClO, I add the prefix hypo, and I have hypochlorous acid. Now let's look at some of those on the bottom of the screen. It says those are the 6 most common ternary acids. So if we start with nitric acid, we know that nitric acid came from nitrate. And we know that nitrate is NO3 minus. With that negative charge, we need, again, like we did with chlorate, 1 hydrogen to neutralize this compound. And because that's nitrate, that's our representative. So we know that we're going to convert the ATE suffix to an IC suffix when we name the ternary oxyacid that's associated with this polyatomic ion. So HNO3 is nitric acid. If we take 1 oxygen away, we know we're going to change the suffix from IC to OUS. And so HNO2 is nitrous acid. If we look at sulfuric acid, this came from sulfate. And we know the polyatomic ion sulfate is SO4 2-, and that is our representative because of the ATE. We're going to convert the ATE to an IC when we name this oxyacid. Notice we have to have 2 hydrogens over here because we had a -2 charge on sulfate. That's going to require 2 + 1 charges to give us charge neutrality in the chemical formula. So H2SO4 is sulfuric acid. Suppose I subtract 1 oxygen and I have H2SO3. I'm going to change the IC suffix to OUS, and I have sulfurous acid. Now I'm going to leave phosphoric acid and phosphorus acid for you to do later, but I also want you to consider what would be the chemical formula of pernitric acid, what would be the chemical formula of hyponitrous acid, and similarly adding the 2 prefixes per and hypo to sulfuric acid or phosphoric acid and determining what the chemical formulas of those would be, because I often put those on the test as well. So there is a periodic trend of common ternary acids in terms of oxidation state. You notice here we have group 3, 4, 5, 6, and 7 from the periodic table. And boron is in group 3. So if we have boric acid, which came from borate, BO3 3-, then we know that this boron right here is going to have an oxidation state of +3. We could calculate it by saying the hydrogen has +1 times 3 here, which equals +3. And the oxygen has -2 times 3, which equals -6 total charge contribution here. So -6 plus 3 means that the boron has to have a +3 oxidation state in order to neutralize this. In group 4, we're going to have species that have a +4 oxidation state. Both carbon and silicon and carbonic acid and silicic acid would have a +4 oxidation state. And you can calculate that similarly to the way we just calculated boric acid. The oxidation state of nitric acid, phosphoric acid, and arsenic acid, the N, the P, and the AS, so the nitrogen, the phosphorus, and the arsenic would all have a +5 oxidation state. In group 6, sulfuric acid, selenic acid, and telluric acid, the sulfur, the selenium, and the tellurium will all have a +6 oxidation state. And then note when we get to group 7, we have a little variation here. We have a +5 oxidation state. We've just looked at chloric acid, but again, we could calculate this because the hydrogen contributes an oxidation of +1. The oxygen, -2 times 3 equals -6. And so -6 plus 1 gives us a +5 oxidation state for the chlorine. And you can similarly calculate bromic acid or iodic acid. Okay, those oxyacids are a little tough. And so let's drop back down to something that's a little bit easier, and that's naming hydroxide bases. Now, hydroxide is another polyatomic ion. And these hydroxide bases are composed of a metal and a hydroxide. However many hydroxide it will take, which is given by this generic N down here, but that would be in a numeral subscript, declaring however many hydroxides it will take to give charge neutrality to the metal, depending upon the metal's oxidation state. So let's name KOH and CaOH2. Now, the first word in the name of this compound is the complete name of the least electronegative element. And that is typically written first because the least electronegative element is going to come from the left side of the periodic table. It's going to be a metal, and it's going to have a positive oxidation state. So again, just like when we started this whole process on the first slide, you can name these based on metal, not metal, and then hydroxide, or the fact that you have a cation and an anion, because hydroxide has a -1 charge on it. So we say the full name of the least electronegative element in KOH, that would be potassium. And then it's followed by hydroxide. So we have potassium hydroxide. And with CaOH2, we're going to say the full name of the least electronegative element, which is calcium, and that's followed by hydroxide. So the name of that compound is calcium hydroxide. Now suppose we have the name and we're going backwards. Let's just look at an example here, and let's just follow calcium hydroxide. We know that calcium has a 2+ charge. That means that we're going to have 2 hydroxides in order to get charge neutrality here. So we write that as calcium hydroxide this way. We wouldn't write CaOH2 this way because that's telling us we have 1 oxygen and 2 hydrogens there. So that is not the way we would represent calcium hydroxide. We need these 2 negative charges, so we need 2 hydroxide ions. Let's look at something like iron hydroxide and see how we're going to name that. And it won't be named the same way as potassium and calcium hydroxide because these are representative elements and they have an oxidation state that is always the same. Potassium is always +1, calcium is always +2. Iron is a transitional metal. It comes from the D block, and so it's going to have variable oxidation state, or we could call that variable charge, knowing that it's actually an oxidation state. So we need to calculate what specifically that oxidation state is on that iron, because just writing iron hydroxide doesn't tell the person who's writing the chemical formula what the charge is, and they won't know how to write that chemical formula. Iron could be written in a couple of different ways. It could be written as FeOH3, for example. And so if we're naming both of these compounds as iron hydroxide, then the chemist doesn't know if they have iron 2 or iron 3. And the reason that's a problem is because iron 2 and iron 3 behave chemically different, slightly different. And so we need to know which one of those two species it is that we have. So we calculate with FeOH2. We don't know the iron, and so we're after the oxidation state of the iron. We know from the chemical formula there is one iron, though. And then we're going to add that to the OH minus. Well, we know that the oxidation state of hydroxide, because we memorized it, so we don't have to break the oxygen and the hydrogen all apart. We just say we have two OH minus, and each one of them has that -1 charge. Because the compound is neutral, we set this equal to 0. So we have -2 with this. We're going to add that to both sides, and we see that the oxidation state of the iron is then +2. We need to show that when we write this compound. So we're going to use the Roman numerals. We're going to write iron, and then in parentheses, the Roman numeral 2, and then add the word hydroxide afterward. So we're still naming it just like we did above. The only addition is we're adding the Roman numeral to show the charge of the transition metal. Now let's look at some binary ionic compounds. They contain a metal cation and a nonmetal anion. So you could say they are a metal and a nonmetal, or you could say they are a cation and an anion. And you know an example of a binary ionic compound already, and you can use this to fall back on if you see that you have a metal and a nonmetal, or a cation and an anion. You know this in ACl is sodium chloride. So this is a good anchor for you to hold on to in terms of naming these binary ionic compounds. You notice that we said the full name of the least electronegative element, and so that's going to carry through as a rule. We changed the ione suffix of chlorine to IDE so that we get chloride, and that's going to carry through when you're naming binary ionic compounds. So let's name BaCal2, Cl2, and K2O. So the first word again in this compound is the complete name of the least electronegative element. So if we name BaCl2, that is barium. The second word is going to consist of the stem of the most electronegative element, and we're going to add that IDE suffix, or switch out the suffix that's there and use the IDE suffix. So that would be chlor, and then the INE is changed to IDE, just like you did with sodium chloride. So the name of BaCl2 is barium chloride. If we name K2O, we know the full name of the least electronegative element is potassium. And we're going to use the stem of oxygen, which is ox, and the suffix is going to be IDE. So that is potassium oxide. Now, suppose we're given the name potassium oxide and we want to write the chemical formula. Well, we know that we have potassium with an oxidation state of +1 And we know that oxygen has an oxidation state of 2-. So it's going to take 2 potassiums with a +1 so that we have a total of +2 to neutralize that -2 on the oxygen. And that's why we write this compound K2O. Ionic compounds that contain elements with a variable oxidation number are going to be written really similarly to the previous compounds that we wrote that had transition metals. So the oxidation number, the least electronegative element, is represented with a Roman numeral because that's the species that has the variable charge. So let's look at CuS. If we look at CuS, we know that sulfur has an oxidation state of 2-. That means that the copper is going to have an oxidation state of 2+ to give us charge neutrality on this compound. And so we'll put that 2 as a Roman numeral in parentheses, and the name of this compound will be copper 2 sulfide. Again, changing sulfur's suffix to IDE. Let's look at Cu2S. Again, we know that the sulfur gives us a 2- oxidation state. So the 2 coppers have to give us a 2+ oxidation state. But because there are 2 coppers here, we're going to have to take that 2+ contribution to neutralize this compound and divide it by the 2 coppers that we have. And that's going to give us a +1 oxidation state for each copper. So we write that with a Roman numeral 1 in the parentheses. And then again, we're changing the suffix on sulfur to IDE. So we have copper 1 sulfide. Now I just want to point out that this is a mistake students regularly make. And the reason that they regularly make it is because they lose sight of the fact that the Roman numeral represents the oxidation state of the metal or the cation. Because the Roman numeral represents the oxidation state, we cannot just transfer. So what the students will often do is transfer this 2. And remember, that would be going here. You cannot do that. It doesn't work. So we have 2 coppers there, and that's where we ended up with this math over here. And we had to divide the +2 contribution of the copper to this chemical formula by 2, giving us +1 oxidation state for each of those coppers. We also have ternary ionic compounds, and I'm going to make this a little bit easier for you in this course. We're not going to deal with prefixes per and hypo, and we're not going to deal with a variety of suffixes. Now that is the case just like ternary oxyacids were, but I'm not going to ask you about that in this class. I will, however, ask you about those prefixes and suffixes for oxyacids in this class. So again, these species contain a polyatomic ion, or what we might call an oxyanion, because the polyatomic ion is going to include oxygen. So let's look at naming something like BaClO3 and BaClO2. The first word in the name of this compound is going to be the complete name of the least electronegative element. And so you can see that rule just carries and carries. And in both of these examples, the full name of Ba is barium. So in naming both of these compounds, the first thing we're going to say is barium. We know that ClO3 minus is chlorate. So we just say the full name of the polyatomic ion. So BaClO3 is barium chlorate. We know that ClO2 minus is chlorite. So again, we just say the full name of the polyatomic ion following the full name of the least electronegative element. So the name of BaClO2 is barium chlorite. There are compounds in which we have variable oxidation number because we include transition metals, and barium is a representative metal. And so barium is always going to have the +2 charge because it's an alkaline earth metal. But with copper, we can have a variation of oxidation state. So when we're naming this compound, we need to say in parentheses using Roman numerals what that oxidation state is for copper. So if we look at CuSO4, we know that SO4 is sulfate. And we know that sulfate has a -2 charge associated with it. So with a -2 charge on the sulfate, we have to have a +2 charge on that copper in order to get charge neutrality. +2 - 2 gives us 0. So the copper has to have an oxidation state of 2. We write the full name of the least electronegative element, which is copper. We follow it with the oxidation state in parentheses, so Roman numeral 2. And then we say the full name of the polyatomic ion, which is sulfate. So this is copper 2 sulfate. We know that SO3, 2-, is sulfite. Why? Because we memorize polyatomic ions. And we know sulfite also has a -2 oxidation state, which means that the copper has to have a +2 oxidation state to get charge neutrality in that compound. +2 - 2 equals 0. We say the full name of the least electronegative element. It's followed by the oxidation state of the least electronegative element in parentheses in Roman numeral. And then we say the full name of the polyatomic ion, which in this case is sulfite. So that is copper 2 sulfite. And we can also name small binary covalent compounds. When we're naming covalent compounds, we need the Greek prefixes. So this is where the Greek prefixes come in. The general generic form is X subscript N, Y subscript N, because we don't have a metal here. We have 2 nonmetals. So let's name P4S3 and P4S5. If you remember, 4 is tetra and 3 is tri. So that will be tetra. We'll say the full name of the least electronegative element. So tetraphosphorus. And then we'll use the stem of the most electronegative element, and we'll switch out the suffix with IDE. So tetraphosphorus trisulfide is P4S3. And then for P4S5, we start out exactly the same, tetraphosphorus. If you remember, 5 is penta, so that will be pentasulfide. Now, there are a couple of rule variations here, and we talked about them earlier on an earlier slide when we were talking about the Greek prefixes. And one that I want to show you is one that you probably know, and that is carbon monoxide. Now notice we don't say carbon monoxide. We drop that extra O, like that earlier slide had a little note about on the bottom when we introduced Greek prefixes. And also notice something else that's unusual here. We didn't say monocarbon monoxide. So when we have only one atom in the first position of the chemical formula, we don't use the prefix mono. But notice we have only one atom in the second position of this chemical formula, and we do use the prefix mono. Keep this as an anchor because this is a compound you already know. You know the chemical formula and you know the name of it. And so you can go back to it when you need to refresh your memory because you're on a test and you're facing something that looks foreign to you. Also, you know this one, CO2, which is carbon dioxide. And you notice that we have the same situation here where we don't say monocarbon, dioxide, we just say carbon dioxide. So again, no mono in front of that carbon because there's only one and it's in the first position of the chemical formula. In naming hydrate compounds, and remember we said hydrate compounds are not in solution. We do not have a salt in aqueous solution. These are solid salts and they contain H2O as part of the compound. Now when you're talking about math, usually a dot like this means multiply, but in chemistry that dot doesn't mean multiply. That dot means that we have water molecules as part of our salt compound. That's what it's representing. So the first word in the name of these compounds is going to be the complete name of the least electronegative element. Again, following that rule. We use a Roman numeral if that metal or cation has a variable charge associated with it. The second word is going to be the stem of the most electronegative element, and we're going to convert the suffix to IDE. If we have a polyatomic ion, we're going to give the full name of the polyatomic ion. And we use a Greek prefix to indicate the number of water molecules that we have. And then lastly, we add the word hydrate. So let's look at BaCl2, 2H2O. We say the full name of the least electronegative element, so that is barium. And then we use the stem of the most electronegative element, and we add the IDE suffix, so that is barium chloride. We're going to use the Greek prefixes to depict how many water molecules we have. So 2 is di. And then lastly, we add the word hydrate. So BaCl2, 2H2O is barium chloride dihydrate. Let's look at LiClH2O. We say the full name of the least electronegative element, so that is lithium. Then the stem of the most electronegative element and add the IDE suffix, so that is lithium chloride. Because we don't see a stoichiometric number in front of water, it's a presumed 1. So that is monohydrate. So LiClH2O is lithium chloride monohydrate. Let's look at MgSO4, 7H2O. Now we know right away that we still have a representative metal. So magnesium is not a transition metal, it's an alkaline earth metal. Sulfate, we know the name of because we memorized it. And sulfate has a -2 charge associated with it. That means that magnesium has a +2 charge, and that makes sense because magnesium is an alkaline earth metal in group, column, or family 2A. The 7 is going to be hepta, remember, and then we add the word hydrate. So we have magnesium sulfate, heptahydrate. The last one, copper, is a transitional metal. And so the only way we will know the charge contribution of the copper is if we know sulfate. Because we have to know the charge on this polyatomic ion. It is 2-. When we know that, we know the copper has to be 2+. And so we're going to put Roman numeral 2 in parentheses right after the copper. 5 is penta, and then we'll add the word hydrate. So this is copper 2, sulfate, pentahydrate. So here are some more examples. Let's go through these examples. And you should be able to use these and other examples in this lecture to practice until you really know the nomenclature that's included in this lecture cold. And then you move on to the worksheets. And then you move on to the next lecture series. And then lastly, you can be working through the lab all the way through this week. So HF gas and HF aqueous. So this is a binary compound that contains hydrogen. So the gas will be hydrogen fluoride, and the aqueous will be hydrofluoric acid. Remember, you know HCl, hydrochloric acid, and so hydrofluoric acid is going to be named just like that. Again, we have binary compounds that begin with H, and one of them is a gas and the other one is aqueous. They look a little different because we have 2 hydrogens on each of these, but the rules for naming them is going to be exactly the same. So the first one being a gas is going to be hydrogen sulfide, and the second one being aqueous is going to be hydrosulfuric acid. Now we have oxyacids, ternary acids, H3PO4, H3PO5, H3PO3, and H3PO2. And there's a note saying these are all aqueous solutions, so we know they're all acids. We want the representative polyatomic ion, so we know which one we start with. We know which one will be converted from an ATE to an IC. So from memory, we have PO4 3-, which is phosphate. That is our representative, and we're going to convert that ATE to an IC. We need to add the 3 hydrogens to neutralize this -3 charge. So H3PO4 is phosphoric acid. Now, from our representative, it looks like the next one here, we're adding an oxygen. That means we add the prefix per. So that would be per-phosphoric acid. The next one looks like we're subtracting 1 oxygen from our representative because we have 3 oxygens now. So H3PO3 is going to be phosphorus acid. The next one, we have subtracted 2 oxygens from our representative, and so we need to add the prefix hypo, and we have hypophosphorus acid. This one, these 2 are hydroxide bases that we're going to be naming. One of them is a representative metal, and the other one is a transitional metal. For the transitional metal, we're going to have to include its oxidation state in parentheses. So we have to figure out what its oxidation state is. And the only way we can do that is if we memorize that hydroxide is OH-, and it has a -1 charge associated with it. Because there are 3 of them, we have -1 times 3, which gives us a total contribution of -3 for the hydroxides, meaning that the iron has to be a +3 oxidation state. So we're going to put that 3 as a Roman numeral in parentheses right after we write the full name of the least electronegative element. So it's iron 3, and then we add the word hydroxide. Now the other one, NaOH, is going to be really straightforward because it's not a transitional metal. So we say the full name of the least electronegative element, and then we add the word hydroxide. So that is sodium hydroxide. Here we have CaO, Mg3P2, and Zn2C. So we're going to say the full name. Again, these are binary compounds. There's a metal and a non-metal. So that's the first thing we're looking for. Calcium is representative, magnesium is representative, and zinc, although it's in the transition block, zinc will always be a +2, as you learned when we went through quantum mechanics and orbital diagrams, because when zinc loses 2 electrons from the s orbital, its d orbital is completely filled, and that is very, very stable. So zinc will always be a +2. So we don't write that in parentheses with a Roman numeral because there isn't variable charge on zinc, even though it's in that transition metals D block. So we write the full name of the least electronegative element. For CaO, that would be calcium. And then we follow with the stem of the most electronegative element, and we give it the IDE suffix, so that is calcium oxide. The next one, magnesium, full name of the least electronegative element, and that is followed by the stem with an IDE suffix for phosphorus, so magnesium phosphide. The last one, zinc, is the full name of the least electronegative element, and again, zinc doesn't behave like a transitional metal, even though it's in the D block. So we say the stem of carbon and add the ID suffix. So that is zinc carbide. Now we have nickel NiF. I almost gave it away for a second. NiF2, and then COBr3, and then CRS3. Now, the thing with nickel is nickel often will have only one oxidation state as well. And so oftentimes nickel will not be seen with its oxidation state written in parentheses. So we have two fluorines. That means that the nickel has to have a +2 oxidation state. And in this case, you can include it or exclude it. So here it's nickel 2 fluoride, but if you had written nickel fluoride, that would be correct as well. Cobalt, on the other hand, is in the transition metals, and cobalt will vary. So we have 3 bromines, each one with a negative charge. So the cobalt has to have a +3 oxidation state. So that is cobalt 3 bromide. And then the chromium, we know that the sulfur has a -2. And there are 3 of them. So that is a -6 charge contribution from the sulfur. That means this chromium has to be a +6. So that is chromium 6 sulfide. Here we have KMnO4 and FeSO4. And so potassium, as you know, is representative. Iron is transitional. We need to know the polyatomic ion in both cases here. This is permanganate, MnO4, and we know that MnO4 has a -1 charge. Potassium has the +1 charge, but because potassium isn't transitional, we don't have to show its charge. We say the full name of the least electronegative element, which is potassium, and then we say the full name of the polyatomic ion. So that is potassium permanganate. The iron has variable charge. Because we memorize sulfate, we know that sulfate has a -2 charge. That means iron, in this case, has to have a +2 oxidation state. So this is going to be iron 2, and the full name of the polyatomic ion, sulfate. Now here are some species when we look at them: phosphorus, oxygen, sulfur, fluorine, nitrogen, and oxygen. Those are all nonmetals. So we're going to name them using the Greek prefixes. 4 is tetra, 10 is deca. Remember we said on the very first slide that we lose that O and we lose that A just to make things easier to write, easier to say. So this is going to be tetra phosphorus decoxide. We lose the A from deca. The next one is S2F10. 2 is di, 10 is deca again. So that is going to be disulfur. We say the full name of it, decafluoride. And then the last one, N2O4, dinitrogen tetraoxide. That wraps up our lecture on nomenclature. If you have any questions, you can email me or bring your questions to Chem at Night, and we can discuss them together as a group.